But let's not deter that. Eunji paid 100,000. We're going to talk about magnets. Okay, so first things first, what the frick is a magnet? Well, in order to explain to you what a magnet is, I'm going to have to explain to you what electric charge is. That person has been here since August? Yeah, I don't fucking care. I don't care. Okay, so let's talk about particles. So there are two types of particles. There are two types of charges in the universe. Positive and negative charges. Negative charges are like electrons. Hold on. And positives are things like protons, which we will just represent with a P. I'll also add a plus, I guess, for that. So there are also different types of charges of particles. There's like positrons, and there's also like... hold on, actually, let me add the audio here so we aren't just immediately just, audio application. Here we are. So we aren't just having like this. I'm just going to add the, there we are. We're going to have a little bit of music. So, these things, positive and negative. Now, what each individual atom does, that they will have a positive charge, is that they will emit this field that we call an electric field. Which basically, all you can think about it is like, it's a field that points outwards from them in every direction. Positive, it points away. Negative, it points towards. Now, how do we define which way a field points? Well, positive and negative charges have these interesting properties where positive and negatives, they will attract. They will move towards each other. So you define an electric field based on, if you were to place like a proton, like right here, what direction would it move? If it's close to a positive particle, it wants to get away from the positive particle, so it will move away, so the arrow points away. And if it wants to move towards a negative particle because it's a positive charge, it will point towards the charge. It's that simple. That's electric fields. But how the fuck does magnets get into this? Well, you see, all it takes to create a magnetic field is you need one charge, and it needs to move. That's it. A moving charge will always produce a magnetic field. And that's because a magnetic field is actually an electric field. But you can think of a magnetic field as like an electric field that's constantly moving. So it will just slowly go there, which will cause an influence on the particles around it. So how does a typical magnet work? Well, magnets, if I were to draw one really quickly. Magnets very plainly are divided into a north and south pole. I'll red this up for you. Red and blue. Which, very quickly, if I were to draw the magnetic lines, they would go something like this. Where they would loop back around and they would go there. Where they would protrude outwards. That's very basically what a magnet is. But the question is why is a magnet like that? Why does it go from north to south pole? You can kind of think of north/south positiveness as kind of like positive and negative charges, but this north/south pole is how the charges move that distinguishes whether it's north or south. All right, and here we'll get into a little bit of equations. We're gonna do a little bit of equations. If we want to know what the magnetic force is, period, that is the charge of the particle, which we call Q, times the velocity of the particle, V, and then we multiply that by the magnetic field. So this tells us, for example, what force this positive charge feels right up here. Draw circles, just in situation, boys. If we know the velocity that this thing is traveling at in what direction, and if we know its charge, Q, and if we know the strength of this magnetic field here, B, we can calculate what forces that particle will extend, and it will go off into a direction. Now, you may be asking, what are these little hats I put on? Those are vectors. They denote direction. The only thing important for the discussion is that QV cross B will give you a force perpendicular to the magnetic field and the velocity. That's it. So, for example, if I have a magnetic field a velocity going in this direction, magnetic field going in this direction, and my particles here with a charge Q, what happens is because this is a two-dimensional plane, it's hard to realize it, but what happens is that it will experience a force directly out of the monitor. So if you're looking at the screen right now, the force is pointing towards you. In physics, we usually denote this with a circle with a dot in the front. And then if we want to denote that it's going in, we do a circle with an X. But that's besides the point. So because magnetic fields and particles represent, like, the force a particle will feel is perpendicular to both velocity and magnetic fields, this is actually the defining property of how we get these little squiggly lines right here. So let's go back down here. We don't need this anymore. We'll delete all of this. But we'll keep the magnet. We'll keep this down here for reference too. So, now, let me ask you, in an order's approximation, what is an atom? Okay. So, an atom is... It is a positive nucleus surrounded by a negative electron. And for the sake of this argument, this doesn't hold up quantum mechanically, but it's a very similar effect, is that we can approximate the atom as an electron that orbits the nucleus. And if it's orbiting in a circle, based on our equation right here, if there was a particle within the within the center of this magnetic field, basically, hold on, let me just do this real quick. The magnetic field points up, it would point right, now it would point out. Basically what happens is that there is a magnetic field that points exactly outward. So this would be the magnetic field in the center. Velocity is going this way, for example. So, hold on, let me just get this. Bam, 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 bam. Magnetic field will point outwards. So that's why, so you can think of each little individual atom as a bunch of small little circuits where this electron moving in a circle is like a wire, for example, like kind of like in electricity. And this velocity will produce a magnetic field. So what happens in this magnet is what we have basically, if I were to do this and zoom in, we have a bunch of particles aligned here. Let me just do this. That are basically all spinning in the same direction, which causes a macroscopic magnetic field to exist. The whole reason why, in physics, we didn't know anything about magnetic or electric fields was because you needed a lot of atoms spinning in the same direction to make a magnetic field. So when all of them are aligned like this, you get that. And then, of course, in the bottom, we have atoms spinning in the opposite direction, which would be this way. So because they're spinning in the opposite direction, basically what happens is it generates a magnetic field upward, which wraps around to go to the magnetic field below, which is also pointing upward. Because you can think of perspective-wise, like if you were to rotate a little circle of current 180 degrees, it will still point the same direction, despite it, you know, because basically what you think about it is all the magnetic field is flipped, but also so is the direction of the electron moving. So so like negative times negative equals positive, both are up. All right, cool. So that is why magnets exist, because there are certain materials that exhibit this little effect right here of an electron going around a positive nucleus is a pretty valid approximation. So this happens in like your coppers, your white, we call excuse me, that's not copper. No, it's more like some degrees of iron and other stuff. Palladium, does it? I can't remember all the metals at the top of my head, people. Okay, this is Raptad and Lizard guesses. Will monopoles be covered in this lecture? No, because not one has ever been seen. Go fuck yourself. But okay, basically, what Bubble said, if you want to know what a magnetic monopole is, a monopole is what happens if you have a single magnet, just a single magnet, that has only a north pole or a south pole. Both are equivalent in this scenario. So, if there exists a monopole with one north pole and one south pole, that actually has huge implications for physics. And I can't really work through the math right now because there's a big proof about it all. You can look this up in your spare time. This is your homework. But if there exists literally only one magnetic monopole in the entire universe, there only needs to be one to exist. We can... This will explain why energy is quantized, which is a big why of the universe. The implication of energy is basically it's like... think about it this way. Energy isn't a spectrum. It's not like gender. It's not like, I don't know, math. But basically, you can only divide energy into such small segments before you can't divide it any further. Kind of like how you can take atoms off the table and keep splitting a table in half, but eventually you won't be able to split it in half anymore because it will be down to just an atom. Energy works the same way. You can only have a certain amount of energy. If you have a little less than it, no, you can't. Doesn't exist. You'll have either 0 or this minimum amount. And magnetic monopoles explain that. There's a proof out there somewhere. I don't have it committed to memory. What was I on about? I was gonna do something else, right? I was gonna talk about something else with magnets. But yeah, what Bubble said, nickel, cobalt, iron, these are all atoms that are susceptible to be magnets because they are within close enough approximation to this model of the atom. Alright, I guess you're just asking, it's like, well, how does magnets get made then? So this will be the last lecture, the last part of the lecture, where we'll explain how magnets get made. So basically, what we need is a block of iron first. Just grab your random block of iron. And if you grab a random block of iron from just anywhere in the universe, it'll likely have a bunch of atoms that have magnetic fields that point in, like, every direction. It'll just have it. So basically, on average, statistically, because each atom's pointing in a random direction, it wouldn't be a magnet. It would have no universal direction, kind of like these things. Kind of like this one. So, how do you make it if you just have a block of hammer? Well, what scientists do is they hook it up to a machine where you can think of it approximately as they expose it to a super strong magnetic field. Because that's what we discussed. Magnetic fields are just caused by moving charges. So what they do is that they, like, shove so much current into these plates, above and below, that it induces such a big magnetic field, such a strong one, that it slowly starts to align all these atoms so that they come together to have this increased effect of a magnet. And then so we'd have, like, a south pole here, a north pole here, and all because it's been blasted by a magnetic field, which will then cause it to become a north and south pole. Any questions from the chat on this lecture of magnets? I hope you're happy. That was like 10-15 minutes on magnets, on how they work. You're still confused? Magnets are caused by by particles going whoop, 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 and then spinning. There you go. That's the TLDR. Do electrons and protons collide? That is a fun question. They would try to collide. So basically, if an electron and a proton, this is not accurate. Electron is small, a proton is fucking big. If they ever collide, they'll just bounce off each other. They don't annihilate, they just bounce. And the reason why they don't annihilate is actually to have to do with particle physics, not magnetics. But basically, they'll have a collision. And basically, I guess another thing is that if the energy allows it, if there's a positive charge here, a proton and an electron, if they ever collide, what happens is actually that the electron will kind of get absorbed by the atom, and then it will join its orbit with the other electrons. That's what will happen realistically. Why does that happen realistic, and why do they not annihilate? Well, there's this thing in physics called the Pauli exclusion principle, which means that two... What's it called? Is it leptons? No, fermions. Two fermions cannot occupy the same space. So therefore, they can't go into the same space to collide and annihilate each other. Because that isn't allowed by particle physics and some rules with quantum. But the electron can join the proton's orbit, or if it's high enough energy, it will just bounce off it. What's up, Burke? Guydoc? So yeah, if you want me to explain Pauli exclusion principle, save up another 100,000 points.